Okay, so we will look at the questions for this. This is the question coming from the some selected past year questions up from the polar coordinates there. Okay, so let's look at the different questions here. Okay, so the first one here we have got the two curves. Okay, they gave us the two curves here. So you can see one is like we have got r is equals to a, and then another one is like we have got the r is equals to 2a cos 2 theta. And in this case, the theta here is from 0 to 1 over 4 pi. So where a is a positive constant, so we need to sketch C1 and C2 on the same diagram. So there are two different types of the questions. So basically, for polar, right, one could be like they already asked us to sketch in the first part. So means that the question should be very easy. I mean, this graph should be very easy to sketch if they already asked us to sketch in the first part. If the sketching only comes in the last part, so it means that the curve might be a little bit more complicated to sketch. So we have to use the previous info to sketch. This is a case where in the first case, in the first part, they already asked us to sketch. So it shouldn't be very difficult for us to do. So also another thing that we need to take note is that they have the value of the data. So when we sketch the value of the data, so of course we could actually start by looking at like the R against data curve first to see what is the pattern of the R. So this is from 0 to pi over 4 here. So our R goes from 2a to the 0. Okay, so we can actually sketch it. So as we actually sketch them, the C1 is R is equals to a, so it is actually a circle that is having like the radius of a all the time. And then for the C2 here, right, we just need to sketch a little bit here. So we have got like, okay, when the data is 0, we have got the R is 2a, and when it comes to the data equals to pi over 4, then you actually have the R here actually goes to the 0 like this. Okay, so that's the sketch for the first part. So the curves C1 and C2 intersect at a point with the polar coordinates A and beta. So state the value of the beta. So they will intersect at some point somehow. So with that, we just have to intersect, find the intersection basically. So equate the two R's there and try to solve for the data here. So the value of our intersection here will be pi over 6. Okay, when we actually try to solve the intersection. What else? Okay. The next part, okay, it is to find the area of the region. So the area of the region here, right, is we have got, we want to find the area which is going from 0 to beta, and then the arc, okay, from theta to beta, and then from theta to 1 over 4 pi, okay, is we have this value, okay, for the area. So basically, what do they actually want to look at is something like this. Okay, so it's actually like this part here, as you can see, the gray part. So this is what the question really wants us to prove from there. So with that one, okay, we know that we are going to do some integration. Okay, of course, for the first one here, right, this is actually the area of a sector. Okay, this is the area of the sector that is actually coming from. Okay, so you can see this is like two parts here, right? One part of it is actually like this sector, which is from the circle. So for the circle, right, you can easily use the area of the sector to find that. Okay, so this is a half r squared d theta, half r squared theta. So that would be the first part. Okay, another part we have is that the very small part, this part here. So this small part is actually starting from the theta equals to pi over 6 up until the theta equals to pi over 4. So this part of the area actually belongs to the C2. So we need to integrate the half r squared d theta for the C2, and then we integrate from the pi over 6 to pi over 4. So read the questions carefully. Yeah, my figure here might not be really able to show the area clearly, so you can draw yourself. Okay, and then you will see where is the area. So basically after that, okay, once we actually simplify everything, like when we actually expand everything, and then when we actually use the double angle formula, okay, this is what we get. And once we use the double angle formula, we could just integrate easily. So later on, it is just to sub in those values of the theta, okay? And we will actually have this value, okay, after we evaluate those things like a 2 pi over 3 for the sine. So eventually at the end here, we should be able to get the value here. Okay, so that's for our first question. Next. Okay, so this is a question that is slightly challenging, I would say. Right. So use the identity which is given to show that the two sine theta, and then we have got like the cos of theta minus 1 over 4 pi is given by this expression. Okay. So first is to actually use the identity given. So this is like the P and the Q. Okay. Which we can actually get like sine of the P plus Q and sine of the P minus Q. Okay, so in the next part, right, the second term, okay, we know that is a sine 1 over 4 pi. So sine 1 over 4 pi here is 1 over sec 2, of course. So we are getting the 1 over sec 2 there. So how do we really like get the first thing here? Okay, so from a sine, okay, how do we actually get the cos thingy here is that we are using the property where if you have got like sine theta, it is actually equals to like cos of the pi over 2 minus theta. So in this case, right, when we replace this theta inside the sine with the pi over 2 minus theta, so it actually becomes the cos already. So this is to use this identity, or we say this relationship between the sine and the cos. Okay, then after we do that, right, then only we are able to actually get something like this. So we get something like 3 over 4 pi and then minus 2 theta. The next part is that we are using another like a result already. So this is like cos of a negative theta is the same as a cos theta. So it means we can actually just like take the negative of the angle inside here. It will still like be the same thing. So we get this 2 theta minus 3 over 4 pi. Okay, so it's more on the trigo results lah for the first part here. Okay, this is how we prove it. Okay, so in the next part, so it's actually a polar equation. Okay, so a curve has the polar equation, which is r is equals to 2 sine theta and then cos of a theta minus 1 over 4 pi. And the theta here is from 0 to 3 over 4 pi. So sketch the curve and state the polar equation of its line of symmetry, justifying your answer. A lot of things that we want to do, that we need to do here, in fact. It's quite, demanding for this curve here. Okay, what happens is that if we want to sketch like this curve, right, it's actually like this thing, 2 sine theta and then this cos theta, whatever. But in that way, we want to sketch it, we are looking at the right-hand side here. So this is why they actually ask us to prove it. Okay. In fact, if we actually want to like draw this graph, right, even like if it is just like a usual trigo graph, it also takes us a bit of time to actually like get this. Okay. So to get that thing, quite a bit of thing that we need to do from here. So it is to start from what we have in the r is equals to cos theta. This is what we get. Okay. And we are doing some transformation here. So the theta becomes like a theta minus 3 over 4 pi, means we move the graph to the right, okay, by 3 over 4 unit. This is what we get. And then the lowest value that we have here is 1 over sec 2, okay, because we are actually like just drawing until like the negative 3 pi over 4 and the 3 pi over 4 here. And then the theta now becomes 2 theta. So you can see the x values here are actually the theta value here, the theta value here actually being halved. So we get 3 over 4 pi. And the last part is actually like when we actually add the 1 over sec 2 to this whole thing here. So when we actually add like 1 over sec 2, then this is the final result that we're actually getting. Okay, so this is how we actually get this r against theta curve. Okay, it's not that direct, in fact. So with this r against theta curve, then we're actually able to see this would be our polar curve. So the r is like, okay, it goes from 0 and then it goes to the 1 plus 1 over sec 2, which is the highest r or the maximum r, when we have got the theta is equals to 3 over 8 pi. So this is the line for the theta equals to 3 over 8 pi. And after that, it is the same. So when we go from 3 over 8 pi to 3 over 4 pi, So this graph is going from the maximum R back to the 0 again. So this is the graph that we should have. So when we show the graph, right, of course, these important lines like 3/8 pi and also the 3/4 pi, we must actually show it. And because this is symmetry, yeah, so when we sketch the graph, make sure that it is symmetry. Okay, maybe my graph is not that nice yet, but just make sure that you show the symmetry. Okay, so other than that, the question also mentioned about like we need to state the polar equation of the line of the symmetry. So really go and state that. Okay, state that. And the question also say justify the answer. So when we want to justify the answer, we need to really say something like why it is the line of the symmetry. So we could say something like, okay, when the theta equals to 3/8 pi, the R is actually having like the maximum value there. Okay, so that's for the second part. So after that, okay, show that the area of the region enclosed by the curve is 3/8 pi plus 1. This is none other than integration. So let me, okay, just show you the integration here. So here, it depends, okay, on us. We could use the symmetric property. So if in this case, I have used the symmetric property. So if I use the symmetric property, I'm using the 2 to multiply by half R squared d theta. So the value of the theta here is I use from the 0 to 3/8 only. Okay, because I'm just using until the half and then we times 2 here. So I just integrate until the 3/8 pi. So that is what we get, right? Okay. So this is the R, okay, the function R here that we square that. So once we actually square that, right, a bit of the thing that we need to deal with, including like cos square. Okay, so this is like cos square of like a 2a like that. So we need to change it to the double angle formula. So when we change it, just be careful. This is like the a, right? So this is like the 2a here. So all the angles must be multiplied by 2, yeah? So not just the 4 theta and the 2 theta here. So this 3/4 must become like 3/2 as well. So it's a whole thing about the angle there when we actually have got like the 2a there. The rest of it, no issue. Okay, so it's just a usual cost and also a constant there. So not really an issue there. So after that, we get all the costs. Okay, so after integrate, we get all the sign that we substitute the values in. So when we sub the values in, the good thing is a lot of the things you get cancel off. Here we have got quite a bit of the terms that we need to evaluate. So in that case, we just have to be a lot like very careful when we actually sub in all the values from there. Okay, so after that, we should be able to prove that the area is given by this value. Okay, the good thing is that they give us the value that we need to prove, so we know whether we are correct or wrong at the end. Yeah, so it's just some integration work that we need to do very carefully lah. All right. Okay. So the next one. Okay, this is another one. So we have got this curve C, it has this polar equation. So R squared equals to 8 cosecant 2 theta from 0 to half pi for the theta. Find the Cartesian equation of the C. So it is to change from the polar to the Cartesian. Cosec 2 theta, something now we are very, something that we are familiar with. If we actually change that into like sine 2 theta, it will be much better. So once we actually have the sine 2 theta, so just change everything back to the sine theta cos theta. So we use a double angle. And for this, we have got like r sine and also times r cos, which we actually get like the xy is equals to 4. This is our Cartesian equation. So what happened next is that, okay, we want to sketch the C. So once we already have the Cartesian equation, right, then it's easy for us to sketch for the C already. So this is basically like a reciprocal graph. So y is equals to 4 over x is a reciprocal graph. On top of that, just have to be careful. They just want the first quadrant, okay, from 0 to half pi. So just sketch for the curve in the first quadrant. So this is just like the reciprocal graph. Okay, so as easy as that. What else? Okay, integration. determine the exact area of the sector bounded by the curve between the 106 pi to 103 pi, and then the half line 106 pi to 103 pi. So basically it is something like this lah. So it's this part. Okay, it's just this part. So nothing much that we have to worry about when we actually try to integrate it. So this is what we get. Okay, so integrate like 8 cosecant 2 theta. Okay, for this, right, they already tells us that, okay, we can actually use a result. So given that integrate a cosecant is the ln of a tangent half x. Okay, so if that is the case, then we actually integrate the cosecant 2 theta, then we will actually get a ln of a tangent theta. But you just have to be careful this one. You need to divide by 2 because you have got a 2 theta here. So whenever you integrate, okay, you need to divide the term by 2. So this is why we actually get a 4. Okay, so the formula is like cosec x. When you integrate, you get a ln tangent half x, right? But if you have, this is a 2 theta, okay, yes, the angle half x here, you get a theta, but this 2 theta itself has a 2. So this is why you need to divide by 2 here. Okay, if you don't do that, you might not get the correct answer there. So after that, right, okay, when we sum in the values and we evaluate the like tangent like 1/3 pi and also the 1/6 pi, right, this is what we get. And of course, okay, let's see what the question wants us to do there. Okay, nothing much, but we just want to determine the exact area. So of course, if we could simplify the stuff here, right, we just try to simplify from that. So this is a ln Z3. This is a negative ln 1/3. The second term here is actually become like a ln of Z3 as well. Okay, it's actually becoming a ln of Z3. So overall, it's a simplifying thing lah. Okay, from here, we get 2 ln Z3 plus another ln Z3, which is we get like 4 ln Z3. And if you actually move the power, the square root, okay, to the front, so we get 2 ln 3. Okay, the square root here will become the power half, so we can move it to the front to multiply. So this is the simplest constant that we can get from here. Okay. Okay, we can look at the next one also, which, okay, this is a curve, okay, that has like a modulus of a cos theta, and they need us to sketch it from 0 to pi. So the curve has got some intersection that we need to find the polar coordinates of those intersections here. So to find the intersection, equate the two r's there, solve it. So we're actually dealing with like the modulus of the cos theta is a half, which means that the cos theta is a plus minus half there, which we can actually have got like the theta is pi/3 and 2 pi/3 for the theta. But of course, we need to find the value of the a there. Okay, so of course, because like the r is already equals to a, right? So the r value must be an a lah. We don't need to actually do further calculation. In fact, we can just take the value of the r, which is the a, straight away. So this is the polar coordinates where they intersect. So next is sketch the C1, C2 and their line of symmetry. Okay. So of course, for the C2, we could actually use a little bit of the r against theta curve to see the pattern. And then the next one here is that, okay, we have got the C1 is a circle. Okay, but here only until like pi, from 0 to pi. So it's a semicircle for the C1. For C2, it looks something like this. Okay, so from this curve for the r against theta curve, for the pattern here, we can actually see that this is our C2 curve. And it further verifies that it has got the intersection at this angle, pi/3, and then it has got an intersection at the theta equals to 2 pi/3 as well. Okay. If you don't show the intersection, it's fine. What they really need us to do is that, okay, we really need to show the symmetry line, okay, the line of symmetry. So make sure we actually show this, okay? Because what happened in the polar is that, right, usually, right, okay, what is given in the mark scheme is that they will usually just use the horizontal axis. Okay, so sometimes they actually don't draw this y-axis there. But because of like this line, it's actually like on the y-axis itself. So you really have to mark it separately and show it clearly that that is the axis of the symmetry there. Okay. What is the next one? Okay. So this is so the region R, okay, is enclosed by the C1 and C2, bounded by the arcs OP1, P1, P2, and also the P2O, where O is the pole. Find the area of the R, giving your answer in the exact form. Okay. So let's see where is the area. So this is the area. Okay. So if we call these intersection points as like P1 and P2, right? So in the question, they actually mentioned that it is the curve that is bounded by OP1, OP2, and then P1, P2. So this is the area that they actually bound, okay, from the description from the question just now there. So what is the next part is we are going to find the area. So as we find the area, right, okay, we can actually see that this is actually some, what is that, some symmetry, okay, some symmetry area here. So that is why here I have used the 2 times, okay, of, okay, so what do we actually have in this case here is, we can look at this area, right, okay, as, so you can see the first term here is actually like half r squared theta. So what I did was, to find this area here, I am using the sector, okay, here is pi over 3, right? So I'm using the area of the sector, which is from, like the theta is from pi over 3 to pi over 2. So this is why the theta here is like pi over 3 to pi over 2. This is the area of the sector, to minus off the small part that I actually like mark the red one here, to minus off this part. Okay, so what is that part that I actually marked just now? It's the area from pi over 3 to pi over 2, okay, of the r squared d theta. So this is the r squared there. So of course, after that, you can expand everything. So at the end here, what are we dealing with is, again, like all the cos square, sin square thingy. So this is the cos square. So just be careful of all the constants and the coefficients there. Okay. For this 2 cos square, change that into the double angle, okay, to in order for us to like integrate from that. So just integrate accordingly. Okay. So once we integrate everything accordingly, and just deal with all the constants, everything, so we're actually able to show this is the area, the exact area. Yeah, so a lot of things to evaluate from here. Okay. Next. Okay. So this is, okay, they gave us like 2 curves again. And we have got like the C1 and C2 are given in the form of like e power theta. So they tell us that, okay, the curve intersect at a point where the theta equals to the alpha. Okay. So first part is to show that we have got this kind of the equation. So this is what we get, okay, when we actually equate the 2 curves there. So the trick here is to try to make it into like a quadratic. But especially try to make it into the quadratic here, right? The equation that has like the e power 2 alpha minus e power negative 2 alpha can be factorized. Okay, so we can actually cancel off the e power alpha plus e power negative alpha. We can actually cancel off from there in order for us to get something like this. Okay, that we can multiply the whole equation here with the e power alpha, that we can actually get the quadratic equation like this. Okay, why can we actually just cancel off this thing? Because this is actually non-zero. Okay, this is something which is non-zero. Okay, this is actually something called like hyperbolic function, which we will learn it in FP2, but they already apply this kind of the idea here without introducing formally what is actually this kind of the function. Okay, but without knowing this specific types of the function, we also can do it as usual one. So we have already found that. And then, okay, find the exact value of the alpha and show that the value of the R is 4 set 2. It's trying to guide us, okay, to give this 6 marks here. So solve the value of the alpha. Of course, this we can use did I do it wrongly? Oh, no, sorry. I thought I do it wrongly. So this is the complete the square. Okay, I actually do complete the square. And then when we actually try to find the e power alpha, it's a 1 plus minus a set 2. So in this case, okay, we are not going to take two values of the e power alpha here because e power alpha must be greater than 0. Okay, exponent value, we cannot have a negative, right? So it must actually take a positive value. So we could only take the 1 plus set 2 for the e power alpha. Then the alpha value here is a ln of a 1 plus a set 2. Okay, and then we are supposed to show that the R value is a 4 set 2. Okay, so we can see the R value here is actually depending on like all the e power data. So the easiest, okay, for us to find the R value in exact value is to look at the first one, the C1. So why are we actually looking at the C1 is because we already have the e power alpha, right? In the C1, we have got e power negative alpha. So the e power negative alpha here is just 1 over the e power alpha. So the e power negative alpha here is 1 over 1 plus set 2. Here, we can rationalize a bit. So once we rationalize a bit, we are getting the e power negative alpha is a set 2 minus 1. Okay, so just do the rationalization here. So the good thing is that when we actually add the two things together, the e power alpha and this is e power negative alpha, when we add them, the constant 1 there will actually cancel off. Then this is why we are actually getting like the R value here is a 4 set 2 in exact form. Okay, a bit of work that we need to do in this case here for the first part. And then, so the questions that is like longer, right, is designed in such a way that if we actually like touch wood, we don't know how to do the first part, we still can use all these things to continue further, right? Okay, so we don't have to worry too much about it. Okay, and then sketch C1 and C2 on the same diagram. This is to actually consider like the intersections and everything. So we already found out, okay, the alpha is actually like this kind of the value. So ln 1 plus set 2. Of course, it is something that is very abstract. We don't know how what is that angle, but we could use the calculator to actually find the angle of that. Of course, in radian lah. So in a radian, you can roughly guess where they intersect. Other than that, if we are not so sure about like how the graph will look like, the last resort for us to do right is to plot values. This is the last resort that we could actually do. Okay, we just need to notice one thing that okay, they will actually have the intersection at the alpha. Okay, so the alpha here is like ln 1 plus 2, right? So this is where they intersect. Okay, just use the calculator to find the value, like the decimal values there. Okay, find the decimal values there, and you can roughly see where do they intersect. Another thing that is actually helping us is that we could actually use the starting point and the end point to sort of like gauge where is the curve. So for example, like if you look at the R1, right, when you sub the 0 and the half pi, right, it gives us this kind of the value. Okay, that is for our C1. So we know that, okay, the C1 starts here when theta equals to 0. It has got the R of a 4. And when we have got the theta equals to half pi, it actually ends at like, the R here is like 10 point something, which is quite large. Sorry, it's here. Okay, 10 point something, right? C2, when the theta equals to 0, the C2 is having the R value of the 0. So you know that the C2 will actually start at the pole. And when the theta equals to half pi, when you sub into the C2, right, the R value is actually quite large, which is 23.1. So it should be further away from here. So by sort of like look at the starting point and also all the endpoints, right, it sort of gives you an idea about the curve already. On top of that, you also realize that, okay, they have got some intersection, which is around this value, ln 1 plus 2. So use those information to actually like sketch the graph here. Okay, although the graph is not something that we are very familiar with, so just try to make use of all the info that we have so far. And particularly in this case, we do not really have an idea how the functions look like. The last resort or the safest way is to always plot values for the theta and the r. Okay, then we can compare how the two graphs will actually looks like. Okay, on top of that, for the part 3, so we need to find the area bounded by the C1, C2, and also the initial line. So the area bounded by the C1, C2 with the initial line is actually here. Okay, so initial line, C1 and C2. So basically this is what we have. So how do we actually find the area here is to consider the alpha. Okay, so this is the alpha here. So we are using the area of the outer curve to minus the area of the inner curve. Okay, so we are using the half r squared d theta. So this is the r squared for the outer curve, which is C1. This is the r squared for the inner curve, which is C2. We can combine them together. So we use the r squared minus the r squared here because they share the same limits. Okay, both of the graphs, the area there is from 0 to alpha here. So when you integrate, right, you don't use the value of the alpha first. So you don't just write the numerical value of the alpha here first, because later on it's very difficult for you to simplify or those kind of thing. Keep the alpha first, and we just see what it gives us at the end. In fact, okay, it is not something that is super difficult to do. Once we actually expand everything here, we get all the exponent terms. So you see we have got all the exponent terms, right? And we can integrate from that. So we integrate all the exponent terms there. So after that, if we have got like all these expression already, which is in terms of the alpha, then only you key in the calculator using the value of the alpha here. Okay, so that at the end you will actually get some value which is like corrected to 3SF here. Okay, in fact, if you learn about the hyperbolic function in FP2, right, this integration could be, you could actually get the exact value here, right? But this is not introduced yet, lah. So you have to do the numerical way, lor. Okay. Okay. Another one. Yeah, this is the last one already. Okay. Also quite a special question. So curve C has a polar equation which is r is equal to a tangent theta. The theta going from 0 to 1 over 4 pi. So sketch C and state the greatest distance of a point on C from the pole. If, like I said, if the first part, they already asked us to sketch, so the graph shouldn't be something that is super complicated. So most of the time would be just strictly increasing or strictly decreasing for the R. So basically, here, this is the graph. I mean, this is a polar graph already, because like I said, it shouldn't be very difficult. We just have to look at like what is the property for the tangent here. Tangent theta is an increasing curve. Okay, it is from 0 to 1 over 4 pi only, so it is strictly increasing. So when it is strictly increasing for the r, and in this case, like when theta equals to 0, the r is a 0. When theta equals to pi over 4, the r is an a. It is strictly increasing. Okay, so you can start like looking at, this is when r is equals to 0, theta equals to 0, and the r just keep increasing until it will actually stop at the theta is equals to 1 over 4 pi. So make sure you draw a line, a dotted line, theta equals to 1 over 4 pi to stop yourself from going further. Okay, and another thing that we need to mention is that they want us to state the greatest distance of a point on C from the pole. The greatest distance happen at this point here. Okay, we know that this is the r is equals to a when the theta equals to pi over 4. So this is the r. So the greatest distance, you really have to state it. They want to see it, okay, in the answer. So the greatest distance here is an a. Part B, find the exact value of the area of the region. So nothing really much about it. It's just to find the area lah that we see here. Okay, it's just to integrate half r squared data. So the r here is a tangent, so we square that. When we integrate from 0 to pi over 4 for the area here, which, okay, we don't know how to integrate the tangent square, right? But we can change it to the secant square. Okay, and we just integrate accordingly. So we can actually get this value here. Okay, right. So part C, show that the C has this Cartesian equation, which is y is equals to x squared over a square root of the a squared minus an x squared. So that is to actually use the tangent. Okay, we split that into like the sine and the cos. So we get like r cos already, and this is we are getting a sine. The sine is actually still lack of like one r here, right? Okay, so we can actually multiply both sides with another r here, in which the right hand side here, the r sine becomes a y already. So this r cos, keep it as an x. The r here, we keep that as like a square root of the x squared plus a y squared. Okay, then we square it. Okay, we square both sides there. So when we square both sides, this is what we get. Okay, and now we try to make y as a subject here. So we expand the x squared. So we have got something in terms of the y as well, right? Now we make y as a subject here. Okay, so follow that, we will actually get this Cartesian equation here. Okay. So what is actually the next part, yeah, is a very interesting part of the question here. So suddenly they ask us to use the the answer in the part B to deduce this value. Okay, so why suddenly we have got this kind of thing here? We observe that this is the curve that we found just now. So what do we mean by when we integrate this curve? So integrating this curve means it gives us the area under the curve for this. Okay, so the area under the curve that we have here is in fact starting from x equals to 0 to x equals to half a sub 2. Okay, we are looking at the area under the curve, so this is when x equals to 0. So where is this, or what is actually this one, half a sub 2? Where is actually our half a sub 2 on these points here? We just need to identify. You see, this is the values of the x, right? Okay, so we could sort of like see that when, okay, the theta here is a pi over 4 and the r here is an a, when we actually sub in the x, sub into the x there, right? So this is an r cos theta. So when we actually sub that, we will notice that, okay, it is actually the x which is like half a sub 2. So this point here, okay, the a pi over 4 here is actually this lah. Okay, it's actually this point. So this has an x coordinate of like half a sub 2. So in the part D, what they ask us to find is they actually ask us to find this one. Okay, but of course this is a 2 marks question and it is a deduce so we are not supposed to just integrate from scratch for this case here. To get this, it is to actually use the idea that we are using the area of the triangle to minus off the area that we have found in the part B. So the remaining part is the area under the curve. Okay, so to find the area of the triangle here, it's of course we are considering the y value as well, because this is like a 45 degree, right? 1 over 4 pi, so the y value should have the same value as our x there. So to get that, we use the half of the base times height for the triangle minus off the answer that we have got from the part B. So that will give us the area under the curve. Here, a little bit of the simplifying that we need to do. So we will actually get this at the end. Okay? All right.